Okay, welcome to part 2 of chapter 15's lecture on thermodynamics. This time we're turning to the second law of thermodynamics. Um, so, what's an irreversible process? One that depends on path. If the process can go in only one direction and the reverse path differs fundamentally, and then the process cannot be reversible. All right, hitting your brakes when you're trying to slow down the car, a great example. You convert energy into heat. That heat is then lost to you. You cannot do work with it, and you have lost energy in the system that is not reversible. Second law of thermodynamics states that heat transfer occurs spontaneously from higher to lower temperature bodies, but never spontaneously in the reverse. Never spontaneously in the reverse. And we talked about how heat is really nothing other than the kinetic energy of the molecules. And once you think about it like that, it makes sense, right? If you can never have a slow-moving molecule crash into a small molecule with low kinetic energy crash into one with high kinetic energy and give it more kinetic energy. That doesn't happen, right? It's always going to go the other way. Saying another way, is impossible in any system for heat transfer from a reservoir to completely convert to work in a cyclical process in which a system returns to its initial state. So, what does this mean in the end? If we end up going in a cycle, that means we come back to the same energy point. So delta U for the cycle, remember delta U is W minus, or Q minus W. Delta U for the cycle is 0. And so for the cyclical process, the work done ends up being equal to the total heat coming into the system, or Q coming from the hot area minus Q flowing into the low area. And we can define the efficiency then as the work done divided by the heat coming into the system, right? A system that's 100% efficient will use up all of that heat to do work, right? A system that has 0% efficiency will do none of that and won't do any work. So this definition of efficiency makes lots of sense. This is the energy, QH is energy flowing into the system. W is the work we do with that energy. The efficiency is the amount of work we do divided by the energy flowing in. And using this definition up here, we can write this as QH minus QC, and it ends up being 1 minus QC over QH. So you can see heat coming in at the hot area and going out in the cold area is what defines our efficiency. In an engine cycle, first the piston compresses, right? Piston compresses. That's here, actually, in B. From point A to B, we compress. The fuel ignites. That introduces heat into the system and does work, right? And then the system piston moves down, and when it moves back up, exhaust flows out. That's the heat we lose that didn't do any work, right? And we're right back to where we were at the beginning, where little air comes in, we compress, boom, we go off again. And so heat comes in with the explosion, right, and it goes out. It goes out afterwards. So this, in between, as the piston is coming down, is an adiabatic process because no heat is flowing in or out of the system, right? Then we have the exhaust go out for going from D to A, and then we go through another adiabatic process up to B, and then we have heat come back into the system, right? And up we go, and off we go. And these are constant pressure, these are adiabatic. Alright, Carnot engine is a theoretical cycle, now called Carnot cycle. It's the most efficient process possible. Second law of thermodynamics cannot be restated in terms of can be restated in terms of Carnot cycle. And so what Carnot actually discovered was this fundamental law. Any heat engine employing the Carnot cycle is called a Carnot engine. So in the Carnot cycle, our most efficient cycle we can go through, we have heat coming in during an isotherm, that's constant temperature expansion. We have an adiabatic expansion, which is constant, that no heat flow during the adiabatic expansion, and then heat flows out along another isotherm, right, from C to B, and then we have another adiabatic compression, i.e. no heat is going in or out as we compress, and this is our Carnot engine. The second and third law form a Carnot engine operating between two given temperatures is the greatest possible efficiency of any engine operating between those two temperatures. Furthermore, all engines employ only reversible process have this same maximum efficiency when operating between the same given temperatures. Okay, the key point here is isothermal processes are reversible, adiabatic processes are reversible, right? Isothermal, adiabatic. So we're going around the Carnot cycle through reversible processes. When we look at applications of this, one that you often see in homes is a heat pump. And we define for a heat pump what we call the coefficient of performance, which is just the inverse of the efficiency. So the coefficient of performance is the heat coming in divided by the work the heat pump does. So in a heat pump, you have heat coming in from a cold source. We're going to have a isothermal expansion. We're going to have an adiabatic compression. We're going to have heat go out as we do an isothermal expansion, and then we're going to do another adiabatic compression. And you'll note this is running counterclockwise while this is running clockwise, right? So in a heat pump we're running counterclockwise. The coefficient of performance is always greater than 1, right? Heat pumps work better if temperatures are similar, not if they're different, but if they're similar, and the cycle is counterclockwise, meaning work was done has to be done on the system to make the cycle run, right? So again, I said earlier, if the system's running clockwise, it's doing work. Here it's running counterclockwise, which means work has to be done to make this happen. Carnot cycle efficiency is defined as 1 minus the temperature of the cold reservoir divided by temperature of the hot reservoir, and these temperatures have to be in Kelvin for this to make any sense. All right, refrigerators and air conditioners are also heat pumps, right? Work is required, input is required for the heat transfer from cold to hot, and this is expensive. So the quality of air conditioners and refrigerators is judged by how much heat they transfer. So the coefficients of performance for a refrigerator is the QC over W, whereas the coefficient of performance for the heat pump was QH over W. Here it's QC over W, and that happens to be QH minus 1. All right, we'll pause here.